Okay, welcome back everyone. Good morning. It's Wednesday, and so we'll continue our semester of discussion on thermodynamics. So again, a reminder, we have discussion sessions today and next week as well. Next Thursday is the midterm, first midterm, 7 to 9 p.m. And at this point, I'll open up the floor for any questions people may have. Or any things you would like to discuss. Okay, so today I'm going to finish up the Joule-Thomson experiment and then move on to a few examples of looking at processes in which we'll apply the first law in their adiabatic processes. And I want to point out something explicitly using those examples. So if there's no questions, I'm going to continue our discussion about the Joule-Thomson experiment. And I started this last class. It was really about answering the question of how enthalpy relates to pressure at constant temperature. And it's an analog of the Joule-free expansion experiment. Okay? And so in the Joule-free expansion experiment, we constructed an experiment where the internal energy of the system remains constant, delta U is 0 or du is 0. So in the Joule-Thomson experiment, we're going to do something analogous where H is going to be constant, and H is a state function. So we have two state functions now, U and H, among the ones you already know, which are temperature, pressure, volume, and things like that. Okay, so in the Joule-Thomson experiment, we have an initial state. We follow a volume of gas as it flows through a conduit, which is insulated. And initially, we have our gas, this volume or this plug of gas that we're interested in on the left side, and it has some volume, T left, P left, and a volume initially on the left side that we're interested in. And this P left is a constant. And then we're going to observe this plug of gas, this volume of gas, go through a porous membrane or a porous material, which is right here. Okay, so this is porous, so it allows, it's not totally transparent to the gas, but it's semi-transparent, if you will, because there's some obstruction in that porous material. So that's why it's there. And that's going to change the pressure on both sides of that material, that plug, that porous plug. Okay. Now we know that internal energy U is a state function. So we should be able to write that in addition to T left, P left, V left, before the gas volume goes through this porous material, there should also be a U left, right? Because we know that as this plug is coming through, it's at equilibrium, it's moving, but it's at equilibrium because the temperature and pressure and volume are not changing. And so because of that equilibrium state, as it moves, there must be some internal energy that's associated with it as well. Okay. Now, as we follow this plug, let's assume it goes through, and then all of that volume that was initially there, or that mass that's associated with that volume, has gone through the porous material. At the end of the experiment, we have gas on the right side, and we have a temperature right, pressure right, volume right, and this volume on the other side will definitely be different than the volume on the left side. And now we can do the same thing. We can write an internal energy on the right side. Okay. So we see here that there's a volume on the left, volume on the right, an energy on the left, and an energy on the right. And the two pressures that are on either side of the porous material are constant. Now, because the insulation is present, we all concluded at the end of last class that there is no heat interaction between the system, which is our gas, and the environment. So in differential form, dq is 0. Whatever this process is, we don't have a subscript for the q yet, but we will see in a moment what it is. But dq is 0 because of the insulation. And so over the whole process then, if any differential amount of heat interaction is 0, then if we were to consider the total heat interaction over the whole process, Q, that has to be 0 as well. And this is going to be important in our analysis. Okay. So I hope everyone took some time to understand that. So let's continue now. So let's look at a first law analysis of this process. Okay, so we have an initial and final state. So we can write the first law for this process in differential form, always. So we have du is equal to dq plus dw, okay? But now what I'm going to do is integrate it. We always start with the differential form, and we can integrate both sides. So now we integrate over the process. And the integral of a state function, if we go from equilibrium state 1 to equilibrium state 2, is just going to be u at equilibrium state 2 minus u at equilibrium state 1. In this case, that u is going to be u right minus u left, okay? Because our second state is the gas being on the right, and our initial state is the gas being on the left. So u2 is ur, and u1 is u left. Okay? And you might say that this is just delta u. Okay, so that's the integrated form of this guy. Right? We know that integrating dq over the process as the system goes from equilibrium state 1 to equilibrium state 2 is going to be q, but that's just 0 because of the insulation. Okay, and we're going to assume it's ideal. And in this case, in this course, you can always assume ideal unless you're told that it's not ideal. It simplifies things when you assume an ideal insulation. And of course, you all know in reality, there's nothing that's 100% ideally insulated. But we can come very, very close. Okay, so that leaves this work term. Okay, so we can integrate the dW from equilibrium state 1 to equilibrium state 2. And that's just the integral of dW as the system goes from left to right. Okay. So let's take a look at this. And that's going to be equal to the work done. Okay, I don't want to write it that way. Let's just take a look at this in 2 stages. Okay, so we're going to look at the work, because this is the one that is kind of the interesting one. Okay, so let's go back to this diagram here. As this plug of volume, or the plug of gas, or this volume of gas on the left-hand side of this porous material, as it goes through the porous material, its volume is going to start at V left. This volume is going to be at V left initially, and then it's going to be 0. Okay, there's going to be no volume as if you just look at that part of the process, that segment of the process where whatever was on the left goes fully through the porous material. And so then there's nothing left on the left. Nothing remains on the left side of this porous material. Okay, so we're going to say that, okay, for that part of the process, what we're going to have is, you know that dW is minus P external times dV. Okay, we haven't said anything about whether this is reversible or irreversible, so we have to write our general expression. And then the volume limits of the integral then are going to be, initially we have V left, because initially we had V left, that was the volume. And then finally, as this thing goes through, this volume element, there will be 0. There's going to be nothing left on the left. So we will have 0. Okay. Right, so that's that first part of that process where the gas disappears from the left side. And as it disappears from the left side, it's going to appear on the right side. Okay, so we have that particular, sorry, what I left out here is that there's going to be a P external for the left side. Okay. Now, as the gas volume appears on the other side, we're going to have another work term because it's acting against the pressure on the right side. Okay, got to act against that, or there's going to be some interaction with that external pressure. So we're going to have here now, initially we had 0 volume on the right. Okay, there was nothing on the right because everything was on the left. Now, as everything on the left goes through, there's nothing on the left, but everything is on the right. So here we'll have V right. Okay, and here we'll have minus P external on the right side times dV. That's our work. Okay. Both of these pressures are constant. Okay, the pressure doesn't change on either side of that conduit, that porous material. So what we can say is that, all right, well, this is just going to be minus P left times the integral V left of dV. And on this side, we're going to have minus P right times the integral from 0 to V right of dV. Okay, and if everyone is not following, just chime in. Okay. Now we can do the integrals over the volume very easily because those are very simple integrals. So here we'll have minus P left. This is just going to be 0 minus V left. And here we'll have minus P right times V right minus 0. Okay, and this is a V. I have a U. This is a V. I have a U. Okay. So this is just minus minus. This is P left times V left. And this is going to be minus P right times V right. Okay, and this arises because the pressures are constant on either side of the porous material. Everyone follow that? So that's our integrated work. Okay, so as this volume of element of gas, okay, goes from the left-hand side, okay, to the right-hand side, these two terms represent the total work that was done for the process. Okay, and it's the integrated form of this work. So now we can go back to our first law, okay, in integrated form. So delta U, which is just U right minus U left, right? That's U2 minus U1, is equal to Q, which is 0, plus W, okay? And I can write Q total here, plus W total, okay? So UR minus UL, Q total is 0 because it's insulated, and W total is this guy, which we just determined. And so that's going to equal P left, V left, minus P right, V right. Everyone follow that? Any questions? Okay. So what I'm going to do now is bring everything over to one side. So what I'll do is I'll keep the U's on this side. So this is UR, and then I'm going to bring the PR, VR term, and I'm going to lump it because that's all for the right. And then we have this UL terms. The UL terms I'm going to also bring over to the left, and I'm going to lump them together, everything with an L. So this is going to be minus UL minus PL times BL is equal to 0 because I brought everything over to the left. And then I'm going to put this together. Okay, there's two minuses there. So that's just going to be, I'm going to write this right term here. Then I'm going to take out the minus sign, and then I'm going to put in here U left plus P left, V left is equal to 0. Okay, and for that second term, if you multiply through by the minus sign, you'll see that you get minus UL minus PL VL. Okay, everyone follow? Okay, but you know that we defined enthalpy as U plus PV. Okay, that was how we defined enthalpy. This is a definition. So what we have here are two terms with U plus PV. In the first parentheses, we have U plus PV for the right-hand side, but the right-hand, which is the final state. So everything on that has this indicator R is for the final state when the gas is moved through the porous material. So this is just H of the right. Okay, this is the enthalpy, right? And then this guy, the second term, is just enthalpy of the left. Okay. But those two equal 0. And we said anything with the right is equilibrium state 2. Anything with the left is equilibrium state 1. That's equal to 0. H2 minus H1 is just delta H. That's the integrated form here, and that's 0. So what we found is that the Joule-Thomson experiment, or process, or experiment, whatever you want to call it, is constant enthalpy. Okay, delta H is equal to 0. And that's pretty good, right? Because we can, and equivalently then we can write dH is equal to 0 along the process. And we integrate this. And by analogy, remember for the Joule-free expansion, we had delta U is equal to 0. So in the Joule-Thomson experiment, we have delta H is equal to 0. And that's exactly what we wanted. That's going to allow us to answer the question that we were interested in, which is namely, what is the partial of H with respect to pressure at constant temperature? Because what that constant enthalpy process is going to allow us to do is set this guy to 0. Okay? Just as we did du is equal to 0 for the Joule-free expansion experiment. Okay, so let's go and answer our question then. And our question was this guy. Okay, what is the partial of H with respect to P? Let's answer that question now, since we know dH is 0. Okay, so let's write that general expression down. So the total of H, which is now, remember from our last class, we had it's a function of temperature, pressure, and N, is the partial of H with respect to T at constant pressure and N, dt, plus the partial of H with respect to pressure at constant T and N, dP. And remember, dN is 0 for the moment, so we won't worry about that term. There would be another term, which would be just the partial of H with respect to N times dN, but we will not worry about that. And we saw last class that this guy, because of constant pressure, right, these partial derivatives are always taken with some constraints. Okay, and when you put a constraint on a partial derivative, it's almost like envisioning a process with a constraint. Okay, and in this case, if the partial of H is with respect to temperature at constant pressure, then we have a constant pressure process. Okay, and we know from relating dH to dQ through the definition of H that this was just Cp of T dt, because the partial of H with respect to temperature at constant pressure and N is the rigorous thermodynamic definition of the constant pressure heat capacity, plus this guy we still have here. Okay, and now I'm going to say that all of this is equal to 0 for the Joule-Thomson. And I'll write that as JT, Joule-Thomson experiment. dH is 0, okay, by construction. You can set up the experiment, you can construct the experiment if you're clever so that this happens. Okay, so that's great. And now we can proceed, just as we did in the Joule-free expansion, to isolate this term, because that's what we want. And then we can see how we can relate that term to experimentally measurable quantities or values. because again, there are no such things as H meters or U meters or Gibbs free energy meters. You always have to determine these kinds of things through indirect methods and things that you can measure, right? Even when you did calorimetry, perhaps in your previous courses, you were measuring delta H as a reaction, enthalpy is a reaction, but really what you were measuring were changes in temperature, right? That's what you measure. You don't measure H. You measure something in between, and then you have a theory, you have a mathematical model that allows you to relate that in-between thing, which is in this case temperature, to the thing you want to measure changes in, namely delta H. Okay? So this is sometimes, but why, so then why do we have theory that, and introduce these things like H and G and U? You'll see the importance of that as we move along. Okay. All right, so let's isolate this partial of H with respect to P for the moment. Okay, so now this is just algebra. Okay, so I'm going to bring in the minus, bring over the minus Cp dt, and that's equal to partial of H with respect to pressure, constant temperature, and dP. And then I'm going to divide through by dP. Okay, so I'll have here minus Cp of T dt dP. But now I'm going to qualify this derivative dt dP in a way, because now we know what kind of a process this is, right? And so this is really the partial of T with respect to P, a constant H. And of course, N is going to be constant in our system. But remember, because H is a constant, when we take this partial, because temperature can change as a function of volume too, so we're just going to say, all right, well, it's going to be a function of H. We're going to take the partial with respect to pressure. So we'll use this constraint here that we have constant enthalpy, and that's really the important one right here. Okay, and that's just equal to the partial of H with respect to pressure, constant T and N. Okay, so again, we wanted to know what this partial derivative on the right-hand side is. Okay, but since we couldn't take measurements directly of H, right, as we varied pressure, because there is no H meter, we had to figure out how we could get this variation using things that we can measure. And everything on the left-hand side of this expression are things that we can measure. The constant pressure heat capacity, we can measure in independent experiments, depending on what our substance is, right? So you have to do a separate set of experiments to get Cp as a function of temperature. And for this experiment, you can always measure T and P and pressure and temperature. That's something it's obvious, everyone, we know this, we can measure them. Okay? We have thermometers and pressure gauges and what have you. So something that we can't measure directly, which is H changing as a function of a change in pressure, okay, we can measure indirectly by measuring changes in temperature as a change in pressure. That's the power of how we can manipulate these partial derivatives. So we are looking at partial derivatives. We know that derivatives are a limit. So in fact, what we can say is, so this is a partial derivative, it's a derivative, okay? And that derivative is going to be a limiting condition. And so we can write the left-hand side in terms of deltas, but take a limit. The way we'll do that is to say, all right, well, we're going to have minus Cp of T dt. And then I'm going to say, all right, well, I'm going to take the limit as delta T goes to 0 of delta T, the constant H and N. And that's going to equal the partial of H respect to pressure at T and N. Okay, so you see what I did here, and I hope it's clear. And going from here to here, all I did was invoke the nature of a derivative, or the definition. Because a derivative really is a limiting thing. A derivative is a beast that is the limit of deltas. Okay, and it's not that complex to understand. You can just, if you when you get a few moments, if it's not clear, just go back and look at your freshman year calc book. It's very simple. So if we take the limit of the delta t over delta p as delta p goes to 0, we'll get this partial of t with respect to p, which is on the left-hand side. Okay? And when we do that, we'll get our partial derivative. So in the experiment, what we would do, okay, so practically, how would you do that? Well, okay, we have our experiment here, okay? All you would do is multiple experiments. Okay, you would do multiple experiments where you would measure the pressure drop. Sorry, you would control the pressure drop across this porous plug. Okay, so you may essentially control the incoming pressure. Okay, so you control the incoming pressure on the P left. Okay, so you control P left. Okay, and that's going to change delta P because for any given P left, you're going to have a corresponding P right. So if you have multiple values of P left, if you do multiple experiments starting with different P lefts, you're going to get different P rights. And since delta P is just P right minus P left, you can control delta P, okay, by controlling PL. And then you measure delta T. You know what the temperature will be coming in T left, and then you just measure T right. And so you do this for multiple experiments, and that really depends on how fine of a resolution you want in your delta P's. You may want delta P's to be 10 bar for between each experiment, or you may want delta P to be 1 bar for each experiment. The finer you make that delta P, the more accurate your estimate of that derivative, right? Because that derivative is a limit as delta P goes to 0. So you want to make that delta P as small as you can get it. So the more data you have, it's always better. And so it's a very simple experiment in theory. All you do is control the pressure, you measure delta T, and you have your delta, you have this ratio that you need to multiple experiments. You can just have many, many data points of delta T over delta P, and then you do a regression. You take the limit as delta P goes to 0, and that's how you would get this partial derivative. Okay. Any questions? That's an experimental approach of how to get something here for which you don't have a measuring device. Okay, so this guy has a very special name, actually. Okay, so this limit as delta P goes to 0 of delta T over delta P at constant H and N. So this is a mouthful, but each one of those things is important, okay? You can't neglect anything in that bunch of words because they all translate to the language of math. Of course, the words are cumbersome. It's very cumbersome to use words, whereas when you use the math, it's very simple. So what this is saying is the limit as delta P goes to 0 or to some very small number of this ratio delta T over delta P, if in your experiment enthalpy is a constant, as well as N, the amount you have in your system, that's equal to this partial derivative of temperature with respect to pressure at constant enthalpy and constant N. Okay. And this guy is defined as, I'm going to use this Greek letter called eta. Okay. Some you might see other Greek letters. So this is a Greek letter, eta, E-T-A, eta. Okay. It's the Joule-Thomson coefficient. This is called the Joule-Thomson coefficient. Okay. So once we define this, we can write, looking at this expression, partial of H with respect to pressure, a constant temperature, and N is equal to minus Cp of T, which is the constant pressure heat capacity, times the Joule-Thomson coefficient. Okay, and you can see here that the Joule-Thomson coefficient is experimentally measurable. And why is it experimentally measurable? Well, right here. You've already explained or demonstrated why. All you have to do is measure delta T and delta P somewhere. Okay? And of course, you would measure Cp as well, but everything on that left-hand side. And since we've defined eta to be that partial of H with respect to P, eta is experimentally measurable. It's something that you can actually grasp in the lab. It's not something that's esoteric, it's abstract or anything, it's just there. Okay? So this Joule-Thomson coefficient tells you the change in temperature with respect to pressure. Okay, so far, is everyone okay with what I've discussed? I'm going to stop or pause just to let you ask questions or bring up a topic for discussion or clarification. Okay. I chime in. I've kind of minimized my chats, so I can't see chats. So just, I love to hear your voices. So if anything is, just chime in. That's fine. Okay.
Clear so far.
All right. So okay, great. So then I'll say something a little bit more about this Joule-Thomson coefficient. So this experiment, okay, why did we do this? Why did I talk to you about it? There's actually three things, and I'm going to address two at the moment. Okay. The first thing is we kind of got more experience and some work, some exposure to how we deal with partial derivatives and total differentials. Okay, and just as we did with the Joule-free expansion, we saw that we could construct experiments that allow us to let these state functions not change, right? In Joule-free expansion, delta U is 0, and in this case, delta H is 0. Okay, so that's one thing. The other thing is a little bit more practical. So this Joule-Thomson coefficient, eta JT, we see is related to how temperature changes. So let me just write this here by itself. Eta JT is just how temperature changes with respect to changes in pressure. Okay, it's really about this rate of change of temperature with respect to rate of change in pressure. Okay. So that's important because we can use this process, and if the process is used, okay, this is a major source of how this process is used, is that, okay, you have a change in temperature across this porous plug. Let me just actually, sorry about that. Sorry about scrolling. So here's our porous plug. Okay, it's insulated. We have a pipe or some, in the diameter of the pipe at the moment doesn't matter, it's just some conduit. So we have a P left, P right, and correspondingly, T right, and a T left. And what this is saying is that because of this porous medium, this porous material creates a pressure differential across the two sides, okay? And what that means is that it causes a delta P, okay? So eta JT gives us some information about what delta T is going to be, or what the change in temperature will be if we have a certain amount of delta P, or a change in pressure, okay? So we know that we can measure this guy. We can measure eta Joule-Thomson by an experiment, and these are tabulated for various materials. You can look in charts, they're published. You can get values for these guys. Eta JT, the Joule-Thomson coefficient. And so in your experiment, if you have a particular pressure drop, okay, you are an engineer, let's say, or you're a chemist working with an engineer, right? You design this instrument with a particular pressure differential or a pressure drop across this porous material that gives you a delta P. You can use the Joule-Thomson coefficient, go and look it up in some reference location, whatever your favorite source may be. You'll find eta JT. And you can estimate now what the temperature difference would be as this gas or as this fluid moves across and through this porous material. And the way you would do this estimate, and so why is the Joule-Thomson coefficient useful? Well, you can estimate delta T given a delta P. Okay, so eta JT is equal to partial of P, partial of T with respect to P, a constant H and N. But what we're going to say is that is going to be an approximation to delta T over delta P. And notice here, this is a very strong way of saying this is an approximation, right? Okay, because we're interested in estimating. Okay, so it's an approximation. That's what this is saying, that this dTdP at constant H and N is just going to be delta T over delta P. Okay, so let me just make this very, very clear. Okay, eta JT is now approximately delta T over delta P at H and N. Okay, and so delta T is approximately eta JT times delta P. This is the approximation or estimate. That's why it's useful. Okay, so if you have a particular delta P that you've designed into a device, okay, this is something that you can get from tabulated values. Okay, you can compute the delta T across this porous material as this gas flows through it. Okay, any questions on what I did here? So this connection to an approximation, right? So we derived the Joule-Thomson coefficient very rigorously from very fundamental first law analysis. Okay, but now it's useful. You see here that it's useful. We did all that mathematics, right, to get at something. But now we see how useful it is because we can get delta T. And why do we want delta T? Okay, great. So now we have delta T. Why do we want delta T? And this is the clincher because this process, if you have a gas, okay, which is at T left, and it goes through this porous material, and now you have gas at T right, for certain materials, the Joule-Thomson coefficient is such that if you have a pressure drop across this porous material, this porous plug, right? What do you think will happen to the temperature if this is a gas? So if the pressure is reduced, what might your intuition tell you about the temperature?
It follows, it reduced.
Pardon me?
It's reduced as well.
Right, it's good to go down as well. And what would the sign of eta JT, of the Joule-Thomson coefficient, have to be if the temperature went down, if the pressure went down? Joule-Thomson coefficient would be?
Negative.
So if both of them went down.
Positive, sorry.
Okay, yeah, that's right. They would be positive, right? It would, eta JT would be positive. And so if we have positive values of Joule-Thomson coefficient, what we'll know is that if we have this porous plug, we let the gas go through, there's going to be a pressure drop. And if eta Joule-Thomson is positive, there's going to be a temperature drop. Okay. So again, eta Joule Thomson is delta T over delta P. And if this is greater than 0, and if delta P is negative, right? Let me just do this ratio. If this is negative and the whole ratio has to be positive, then the top has to be negative as well. Okay, so that means delta T would be less than 0. And if that, in that case, what we can do is we can design a device such that delta T is sufficiently negative, okay, or the temperature reduces to a sufficiently low value that we liquefy the gas. Okay, so if delta T is less than 0, we can liquefy the gas. Okay, and this is the practical use of this whole Joule-Thomson process. Okay, it's a way to take a gas, push it through in a conduit, this porous material, which is an obstruction, okay, that leads to a pressure difference, in this case, lowering of the pressure. And depending on the material, if the Joule-Thomson coefficient is positive, you will have a concomitant reduction in the temperature of your gas. And that's going to liquefy the gas, okay, depending on what regime you are working in. And that's the design problem, okay? But the principle here is that you can actually liquefy the gas by reducing its temperature, by pushing it through this porous material. And this is the usefulness of the Joule-Thomson coefficient, or the Joule-Thomson process. And the way, one place where you'll see this is in NMR instruments. Okay, you have to use very cold temperatures to keep magnets very cool. And so oftentimes you use compressed gases, a lot of your materials like liquid nitrogen or the liquid helium that is required, you don't keep it around in liquid form. You keep it around in a gaseous form. That's why you have these cylinders or these tanks outside of the Brown lab building, right? And what you have to do then is take this gas, you liquefy it, and in doing so, you reach these very low temperatures that allow you to cool things to temperatures that you can't use ice for. Okay. Any questions? So the Joule-Thomson coefficient process is really something that is very practical. It's always, again, it's used in NMR instruments. And I know chemists need to know NMR. And so it's a very applied approach, applied process. Okay, any questions? I said a lot. Or comments? Okay, so this is a very useful way to estimate things. Okay. All right, so now what we have then, I'm going to continue. So great, now we know. So we use a particular process to get at this guy, partial of H with respect to pressure at constant temperature. And we saw that this is just minus Cp of T times the Joule-Thomson coefficient. And now I'm going to introduce the fact that the Joule-Thomson coefficient is indeed a function of temperature. Okay, so this is what we found through the Joule-Thomson coefficient. Let me just reiterate right here. This is what we found earlier in the lecture today, that this partial, okay, and so this is what you have to keep in mind. This was what we're after. The partial is this, remember, right? This is the partial of H with respect to pressure at constant temperature and N. So that was the question we were after. And we saw that it can be related to this. Okay. So what we can do is now write our general total differential. Again, this question came up last time, so I'm going to make sure I state it. Now this is general. This is the general differential, total differential of H, as dH is Cp of T dt minus Cp of T eta Joule Thomson times dP. Okay? And this is really just partial of H with respect to temperature, constant pressure N dT, plus the partial of H so we found through experiment both of these terms. We found this experimentally to be Cp of T, and we found this experimentally to be the combination of Cp of T times eta Joule Thomson. Okay. Two things, don't go away yet. I want to just say one thing. The Joule Thomson coefficient, and this is very important, for an ideal gas is equal to 0. Okay, and we will prove this and we'll see this later on. Again, we need a little bit more machinery to understand how we would prove this. Okay, this is a 0. Okay, so for an ideal gas, the Joule Thomson coefficient is 0. What that means then, okay, what that means is that for the dH for an ideal gas, okay, is just Cp of T dt. There is no dP term because for an ideal gas, this guy is 0. For an ideal gas, this guy is 0. Okay? So for an ideal gas, you would only have the Cp of T dt term. And so only for ideal gas, you can write H is a function of temperature and N only. You don't have to worry about pressure or volume or anything else. Okay, and so this is why this is important. For an ideal gas, you have this relationship that the enthalpy is only a function of temperature. Okay, so H ideal gas, only a function of T. Okay, is that clear, everyone? I haven't proven this yet. I'll prove that later. Any questions or comments? Any questions or comments? Okay, one final thing. Give me a couple more minutes. I just want to, okay. Some of you may be asking, why are we interested in du and dH? Why do I even care? Why did I take the time to write dH is equal to this partial with respect to t, you know, and blah, 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 so on and so forth? Why do I care? Okay, so this is the big picture. I'm answering why. Okay, and the answer is that we want delta H and delta U, and later delta G and delta S, and something called Helmholtz, which is delta A. We want these guys later on. Okay? So, and in order to get delta H, I'll just use delta H as an example. In order to get delta H, we need expressions for dH. Okay. Why? Well, delta H is just the integral of dH from state 1 to state 2. So once we have dH, we can integrate dH from state 1 to state 2 to get delta H, because we want delta H and delta U. Okay, so any way we can get expressions for dH, this total differential of H, that's going to allow us to get delta H. And this holds for all of these state functions that we will see: Gibbs free energy, entropy, and Helmholtz free energy, which we will get to in the coming weeks. Okay, so this is why we're interested in differentials. Okay, these total differentials. Yeah. Okay, any questions, comments? That would be my last point for today. Okay. Um, thank you all for coming and participating and listening to the lecture. I will post it, and I wish you all continued happy week, and I hope everything goes well for you all. I'm going to end the meeting then.
Thank you.
Okay.
Um,
Bye.
Dr. I
Oh,
have
yes.
a question.
Can you
So,
increase your volume, please?
sorry.
Oh,
I have,
it's okay. I got it. It's my fault.
okay. I was wondering, like, what kind of questions do you should we expect for the exam?
Kind of similar to the homework.
Okay.
And there'll be some conceptual questions. You know, just I haven't made up the exam yet, but you know, you might have definitely a first law question. You know, compute work and heat interactions, or what is delta U for a certain process.
Okay.
You might, you know, obviously you'll need to know all the types of processes, right? Adiabatic, isothermal, constant volume. So it's hard for, if you've done the homeworks, I think that will be a good guide.
Okay. So it would be like more conceptual and like kind of like the math problem we have done we do in the homework, right?
Yes, it will be both, right? So there will be some conceptual, yeah, you will need to know concepts.
Okay. That sounds all right. Okay. Thank you. Yeah. Have a good week.
Okay, you too.
Bye-bye.
Any other questions? Okay, not everyone's leaving now, so, okay.